We're very happy to have Luca today from University of Chicago, who will tell us about bound-on equilibration time from hydrodynamic fluctuations.
Okay, thanks Himanshu for the introduction, and thanks for the invitation. It's very nice to be here. So this talk will be about the real-time dynamics at finite temperature in quantum field theories and more generally in interacting systems. So interacting systems at finite temperature thermalize, and they do so with a characteristic time scale, the local equilibration time. This is the time scale for your system to locally reach some kind of thermal equilibrium. What usually happens after that is that hydrodynamics emerges and controls the much slower equilibration towards global thermal equilibrium. So the time you need to wait to reach global thermal equilibrium, will depend on system size. But this local equilibration timescale is really an intrinsic property of your system. And so, so I think I'll just read this. So it's an intrinsic property of your system, which is which in a sense really measures how strongly interacting it is. So I really like this quantity. I think we should care about it, and most of this talk will be about this local equilibration time. So to give you an idea, in a weakly coupled system, you could think of this as just the scattering time, the mean free time between collisions, more precisely the large angle scattering time. And so that at weak coupling, it's always going to be parametrically large. Okay, weakly coupled systems take a long time to thermalize. They mostly just scatter off each other.
Sorry.
Because
it depends on what one means by local, right? So there's some implicit definition, like assumption here. What you
I'll define precisely what the local. But here at weak coupling, it's clear how you would.
Yeah, but so for instance, in this example, it's basically on the scale of what the
collision time.
Right. Yeah. So that's kind of what one means by local in this example.
Yeah, that's what I mean. So just maybe it is for QCD, this would be 1 over g to the 4. This is the time scale. But I would like to have a definition that would work away from perturbative regimes as well. So that will be part of it. Yeah. So here, but this example makes it clear that this time scale can be parametrically long. However, what's appeared in the last maybe 2 decades or so is that systems can't instead thermalize as fast as they want. There seems to be a limit, a quantum limit on how fast systems can thermalize, and this goes under the name of the Planckian conjecture. And this kind of came from both theory and experimental motivation, this conjecture. On the theory side, it came from solvable models of strongly coupled systems, for example, from holography, where quasi-normal modes appeared at this time scale. And again, so here the non-trivial part of the statement is that clearly this time scale can be parametrically large, and it looks like if you keep on cranking up coupling, you can make it smaller and smaller. But it seems that this is not the case. That you can't make the equilibration time parametrically small.
Sorry, Luca. How can you imagine a time of equilibration less than the oscillation frequency of a quantum energy? This one over this limit seems, isn't that obvious?
I think it's not obvious because you can have, if you have, let's say, a strongly interacting CFT with no small number, it's pretty clear that this is the only time scale that will appear. But the fact, the fact that you can parametrically, you can have parametrically slow thermalization, but not parametrically fast thermalization, is what makes this statement not obvious.
If the theory is weakly coupled, then it's longer.
Then it's longer.
Yeah, but I'd say that the lower bound is this. That's obvious.
So, well, I'm going to try to prove it. To me, it's not obvious that.
Just very nice, because you need to establish those frequencies, right? So
I
think that's what Ricardo means.
Yeah.
So if you start with a different frequency, to get to that frequency, you need at least that time, right? Because otherwise.
No. So I think the statement is that, well, okay, I'll make it clear in a bit, but the statement is, let's say I look at a correlation function in real Lorentzian time as a function of time. Okay, at very late times, it's going to be controlled by hydrodynamics. At early times, probably not. The question is, when is the crossover happening?
It depends on the coupling.
It depends on but the point is that
it cannot be shorter than the microscopic timescale, which is 1 over t.
But why is that the microscopic?
Because that's the timescale it takes for a quantum to oscillate. To even say,
that's a very kind of, I don't know, that's a very quasi-particle picture. Will that apply to CFT?
I think the prefactor is system dependent, so that's why it's not obvious there's a bound, because it could be that the prefactor you can keep making smaller by
Exactly.
Get a
That's
better
what,
and better system.
That's what
That's
the
why it's
statement
not
is, that there is really a sharp
yes.
defined prefactor here.
Yes.
This bound is not just squiggly.
Yes.
But there is
So I'll try
really-
to make it non-squiggly.
Okay.
I'll try to make it non-squiggly.
And you also say what's T.
Temperature. Oh, this is temperature. This one I'll define. Yeah.
Wait, how do you define temperature if it's on equilibrium? I mean,
So
it's just
it
zero
relaxes
energy.
to a thermal state, and that's the temperature.
The final state is temperature T, the time
Yeah,
takes.
this will be, hydrodynamics is mostly about, well, thermalization, an easier way to understand thermalization is near equilibrium. So there's a sharp notion. Okay. Another motivation for this comes from experiments. You might have heard of this linear and temperature resistivity of strange metals. If you very loosely think of resistance as measuring the scattering rate between particles, then a potential appealing explanation for this would be that these systems are trying to saturate the bound.
Sorry, maybe
Yeah.
you said, and I just didn't hear properly, but I don't know what a strange metal is.
Yeah, so maybe I'm not sure I want to go to. I won't really go into that. This is just a kind of experimental motivation. So it's high temperature superconductors have a phase at temperatures above their ordering temperature, where they have phenomenology that's very different from regular metals, and that's why it's called strange. And in particular, it has this resistance that's and this is seen in many materials, so it seems to not be, it's not a chemistry fact, it seems to be perhaps pointing towards universal physics. That's just a motivation. I want to take a step back and just ask the broader question of whether there exists a quantum statistical mechanics bound on an equilibration time that I'll define in a bit. And what are the principles that go into establishing such a bound? How can we prove this? And I'd like to convince you that the answer is yes. So this might, for those of you who work in thermalization, chaos, and so on, you might see a similarity with the Lyapunov exponent, which is a kind of popular probe of chaos in semi-classical and classical and semi-classical systems. They're kind of similar in that both, if I view it as a rate, both of these rates are parametrically small at weak coupling, and they seem to be bounded at strong coupling. In the case of the Lyapunov exponent, you can actually prove a bound. I don't think it's, again, I don't think it's an obvious bound, but it follows. The bound is provable. But this equilibration time that I'm interested in is well, first of all, it's well defined in general. It's even away from semi-classics. You don't need a large n to identify to extract this.
Sorry, I'm very ignorant. What's the capital N you just referred to?
The number of degrees of freedom. Let's say the number of fields in your system. So this is something you need to extract this other.
It's not related to the number of particles.
It's not related to the number of particles, which is large n. And so this time scale I'm talking about is well defined in general, and it's more experimentally relevant in that it's going to control regular correlation functions, transport, for example, that you would measure in condensed matter systems, maybe the Porphyry constant. But it has also proven more difficult to constrain. And partly this is because of a lack of a sharp definition. So the first part of this talk will be precisely about giving you a sharp definition of this local equilibration time. And just loosely, let me give you the punchline. I'd like to define it as the timescale where hydrodynamics emerges. And we'll try to make this a little bit sharp. Then in the second part, we'll see how detailed knowledge of these kind of modern effective field theories for hydrodynamics allows us to place a bound on this timescale. In a nutshell, the point is that these EFTs have a strong coupling scale. They know about their own breakdown, and that strong coupling scale will bound when they can emerge. And finally, in the last parts, depending on time, I'll tell you a little bit about precision tests of these effective field theories. Kind of similar mindset as that one would use in particle physics, except in the context of chaotic thermalizing systems, where we'll be able to test these effective field theories beyond their kind of leading order predictions. Before we do that, this is based on these papers, so that the precision tests are in collaboration with these people, in particular my student Ruchira Mishra at the University of Chicago. Just to give, so that we have kind of common language, let me just give you a quick crash course on hydrodynamics. This is kind of a poor man's version of hydrodynamics, but we'll make it a little more sophisticated later. So hydrodynamics is basically an effective field theory of conserved densities. The idea behind it is that in a thermalizing system, your system loses memory of most initial conditions, except for things that can't decay because they're conserved. So total charge can't decay, it's conserved, and similarly long wavelength modulation charge densities are almost conserved, right? Their time derivative is related to the gradient of something else. So this operator, the charge density at some small wave vector, is an almost conserved operator. It's a long-lived field. It's going to be light in the EFT language. Now, the continuity relation also involves the current density, spatial current, which is itself not a slow operator. Its time derivative is not given by the gradient of something else. But in an EFT mindset, we can express it in terms of our slow degrees of freedom, in terms of our light degrees of freedom, in the most general way possible. Okay, and that's what one does. These are called considered relations in the context of hydrodynamics. And you just write down the most general thing you can in terms of our light degree of freedom, the density. Okay, the first thing you can write down is this thing that will lead to the diffusion equation, and there will be corrections. So if you just plug this in here, you get the diffusion equation. This is what its solution looks like. This is what a diffusive two-point function looks like. If you inject charge or energy, at some point it will spread like a Gaussian, and there's this overall power law decay, which comes from the fact that you can remember this power. If you integrate over space, total charge is a trivial operator, and that's indeed what integrating this Gaussian will be. So of course there are corrections to the statement. This will be the leading behavior at late times of a density two-point function in a thermalizing system. There will be corrections coming from two things. One is from higher gradient corrections to, for example, this equation. And those, in principle, that's always a controlled expansion, because you can just look at longer distances, later times, and they should give smaller and smaller corrections. There's also another expansion, which is an expansion in fluctuations. To get this Green's function, we have to linearize the diffusion equation and solve it. So these fluctuation corrections, so there will be nonlinear corrections to the diffusion equation. For example, the diffusion constant can depend on the quantity, on the value of the density that's diffusing, or temperature. Let's say shear viscosities depend on temperature. And so that inevitably leads to nonlinearities in these things.
So by fluctuations, you mean here?
Thermal fluctuations.
Thermal. Are there also quantum corrections to this? Yeah.
Yeah, so not really, in the sense that, so once your system thermalizes, it's mostly classical.
Well, mostly correct, but you're talking about corrections.
Yes.
So are there
Yeah.
meaningful quantum corrections?
There are. It's pretty high order. I can tell you what order they would enter, but So yes, but the leading effects are thermal fluctuations.
So if it's supersymmetric,
You could have. Okay, maybe let's talk about this one. The idea is that you have one slow mode for every continuous symmetry you have.
How do you distinguish quantum and classical?
Yeah, so this is very. You could have done this in a classical system as well.
Yeah, but just to understand, like, that's a case question. I mean, I have a nonlinearity and when I have a loop.
Yes.
How do you say that that's classical or quantum?
The loop is purely a thermal that would just.
Yeah, but then I don't understand, how do I distinguish whether it's quantum or classical? What's the definition of quantum in this context?
So the quantum effects I was referring to is that at some order in these hydrodynamic effective field theories, you have constraints from TMS, from the fact that your thermal state. Those would distinguish, have an explicit hbar in them. Quantum, the actual hbar. And okay, so that's kind of.
but those effects from KMS are built in your effective Lagrangian.
Say again.
They are built in the Lagrangian. In the sense you have already integrated out.
You've integrated out. It's not the quantum.
So this Lagrangian has all the quantum fluctuations already integrated.
That's the thing. Yeah. Okay, so let's start. Let's try to define this local equilibration time. So I said before, in a weakly coupled system, I think there's a perfectly satisfying definition, which is to define it as the, let's say, large angle scatter. But I'd like a definition that will also work more generally when you don't have kind of kinetic theory or some kind of weakly coupled particle description. So how do you do this? Let me first say one thing you shouldn't do, which is very tempting to do. Which is to look for correlation functions that decay exponentially in your thermal state. Right? You might kind of think, oh, this is what thermalization looks like. And if you have exponential decay, that's a very sharp way to extract an equilibration time. But the problem with this approach is that actually exponential decay is not generic precisely due to hydrodynamics. So let me just illustrate this with a simple example. Let's take a QFT 5-4 type theory. So this system is interacting. You can turn on a finite temperature. You can even study it at weak coupling if you want. it thermalizes, hydrodynamics is going to emerge. So the stress tensor 2-point function will have this hydrodynamic form. It's going to have diffusive modes. It will also have sound modes, which look very similar to diffusion, but there's a ballistic propagation. So that's what the stress tensor 2-point function looks like at late times, at leading times. So obviously the stress tensor doesn't decay exponentially fast in the thermal state, but it's a hydrodynamic, it's a conserved quantity. Maybe that's not too surprising. So let's try to find some other operators. Let's choose another microscopic operator and look for exponential decay. But the problem is that any operator, there's no quantum number that separates operators that you might like and the stress tensor. So this operator, for example, phi squared, in the thermal state, there's no symmetry that forbids it from overlapping with the stress tensor, from carrying energy density, basically. And so its 2-point function will essentially be the same as the energy density 2-point function, up to a matching coefficient. So it won't have exponential. You could remove this overlap by hand, right? You could consider a funny linear combination of that operator and your energy density, such that you kill this overlap. So this by construction will decay faster than this polynomial, but it still decays polynomially because now there's no symmetry that forbids it from decaying into 2 hydrodynamic excitations. So there's a kind of hydrodynamic pollution of every correlation function. Okay? Nothing decays exponentially in this case. This is a lattice version of that same statement.
So is this because? So okay, go ahead.
Maybe.
If from ADS CFT one gets the picture that things do decay exponentially except by the quasi-normal modes, why is that misleading?
Yeah. So there you have kind of decoupling. Well, 2 statements. First of all, if I didn't have this phi q, I would have a Z2 symmetry, and there the phi operator might have exponential decay. So sometimes you have selection rules that could allow for an operator not to be polluted by hydrodynamics. And often secretly in ADS CFT, we have this thing where you have a scalar phi in the bulk and you assume a Z2 symmetry.
No, but ADS CFT makes it seem like you created an excitation near the boundary, everything falls into the black hole, so it's an exponentially decaying tail. That seems generic.
Yes.
From what you're saying, it sounds very special.
That's right, it's very special. Yeah.
But why does it seem generic?
Because it's a kind of large n exceptionalism. There you don't One over n effects will couple these things, and you'll start having hydrodynamic tails and other.
Large n or large coupling?
I think you would need quantum effects in the bulk to see these
the statements here are pretty general. Doesn't depend on the size of the coupling.
Here that's so this one specifically. Okay, so you could do several things. You could have a scalar in ADS CFT that just couples linearly to the metric, and then you could have kind of a hairy solution where you see the hydromodes in the scalar function. But this effect, let's say you now consider this operator. This would be a 1 over n squared, 1 over n effect.
For an internal symmetry. So the issue there is that thinking particle physics wise, is that operator or overlaps with the Goldstone or not.
I'm not going to call it Goldstone, but
well, soft mode.
Yes, soft mode. Yes.
Okay, it overlaps with the soft mode. So if it was an internal symmetry, I just use an operator that is not charged.
That's right.
Under the thing, and then I would only change the soft modes in pairs.
Yes.
Other than here, you're changing it singly. Right. This is why you get this. You get a single soft mode dominating that correlator.
Right.
Yes.
I mean,
also 2. Okay, 2 is just a different color.
Yes. Yeah.
So that you're saying that also for internal symmetries, I have double and multiple.
Yes.
But it will enter derivatively.
Yeah, there's also derivative corrections, which will, that's right. Yeah, the idea is you choose your microscopic operator, you write down an operator matching equation with the stress tensor, higher derivatives of the stress tensor, multiple functions.
I'm thinking for a superfluid. Let's say you have a superfluid.
Yes.
There, if I write an operator that is neutral under the U1, there I don't see any issue of long distance.
No. If you have in a superfluid, if you have a microscopic operator that's neutral under the U1, it's going to talk to the phonons and it will have long distance.
But if I write it as an ineffective field, there's going to be some derivative.
d phi
squared.
Yes.
And this has one local place, you're saying.
It has phi.
Yeah. It has one local place.
Yeah, I'm just saying they talk.
You just say the current is neutral.
Good. So how can we define this equilibration time if we can't find exponential decay? Well, instead of suffering from hydrodynamics, we should use it. We know what systems thermalize to. Hydrodynamics emerges, and so we can define, at least loosely. We should think of this one way to think of this equilibration time quite universally is as the time scale at which hydrodynamics emerges. This is first a kind of loose definition, but it's appealing because it doesn't depend on the thermalization mechanism. If you're weakly coupled or strongly coupled, it's always hydrodynamics will always emerge. It's often what people who do numerics kind of already do. So let's say you're doing numerics in some spin chain or something, you see at late times a power law, you identify diffusion, and you might kind of compare it to your power law decay. This is how diffusion looks like. This I think is in one dimension, and you would say, okay, when I have quantitative, within 10% agreement with this behavior, that's when I declare that hydrodynamics has emerged. So at least loosely, this is kind of a good working definition that can be used. But we can do better because hydrodynamics doesn't just tell us this leading behavior; it tells us systematically how to, all power law corrections to this behavior, like in any effective field theory. So there's going to be. So this is a kind of, the way I wrote it is an expansion in late times. Here I'm looking at a density 2-point function. And hydrodynamics gives you an expansion, it tells you the form of this expansion. So there's two sources of corrections to this leading behavior. There's the hydroderivative terms I mentioned. In this simple diffusive example, hydroderivatives, let's say I have, they come with two spatial derivatives, and that in diffusion scaling translates into one time derivative or 1 over t. Okay, so hydroderivative corrections give integer powers of 1 over t. And then here, these are these thermal fluctuation corrections coming from nonlinearities in your equations, and those come with non-analytic powers of t that depend on dimensionality. This is the kind of general structure of the expansion. Okay, a term at n loops and L derivatives is somewhere in here. And the point is that these power law corrections each come with a time scale, right? Because you have their power law subclass compared to the leading behavior. So each of them give you a sharp definition, and you can measure these numbers, right? These are kind of transport parameters. You could write down a Kubo formula to measure these numbers, and so those are sharp, offer you sharp definitions of the equilibration time, and those are good definitions, by the way, because these are time scales at which these corrections become order 1, compete with the leading behavior. So starting at very late times where this expansion is controlled, where hydrodynamics emerges. These are timescales at which you've already kind of lost control, right? Where these corrections are very large.
So, and D is what?
D is the spatial dimension. Or this diffusion constant.
Oh, this one's
Yeah, spatial dimension.
Yes.
So if D equal to 1, there is some log.
There's some
log running, right? Because it's
which one?
well, at D equal to 1, there is square root, but also 1 over T correction already contaminated by the third line, right?
This one and this one.
Right, yes.
So we'll talk about it in a bit. You can distinguish these things. You can, in a bit, we'll spatially resolve these. They have different scaling functions. So you can sharply, yeah. I'll talk more about this.
Even in D equal to 1.
Even in D equals 1. 1 plus 1.
So if one of these terms happens to be 0,
yes,
the time scale for
that's right. So you could always fine tune it, right? So indeed, to have a good definition, probably you should say the biggest amount, the biggest such term in the first few, to avoid fine tuning.
Because you want to propose a lower bound on the.
That's right. That's right. So okay, yeah, exactly.
So you're saying choose the biggest out of this infinite set or subfinite set, or what exactly is the?
Yeah. So I think so. Okay, there's going to be we're soon going to extract the clear strong coupling scale for the definition. I would say you could either define it to be the biggest, the supremum of this set, or you could say, well, it's the biggest of the first few, and I don't allow fine tuning beyond. Of course, if you fine tune 8 parameters, maybe you'll make 8 of them 0. So then I'd have to take the biggest of the first 9, and so on. But okay,
You're proposing a universal lower bound on the time scale. So
yes.
it shouldn't rely on things like you're not allowed to fine tune, or you have to.
No, that's right. That's right. So you could just take the supremum if you want.
But then there's infinitely many, and these are probably asymptotic series.
Yes. Yes.
So then the supremum is infinite.
Good. So there's an exponential blow up, but you can take. We know how the exponent grows, so you could take the supremum of the coefficient divided by. In fact, I think I even yeah, you divide. So there's an L factorial, but it's raised to the 1 over L. So these loops have a growth, a factorial growth, and you can take this into account if you want to define this.
So you're going to look at the cluster of these the loops depend on the same with some coefficients for this.
Yeah, and that's what we're going to get the bound from. So indeed, these higher derivative corrections depend on new Wilsonian coefficients. They're very hard to constrain.
But those are not exponential.
They're not exponential burn, but they're hard to constrain. That would be kind of, and maybe so people are working on trying to constrain them, UVIR constraints and so on, but that's subtle. Whereas these lower lines are much less subtle. They're completely fixed in terms of the higher lines by the effective derivative. So there you really can use the predictive power of the effective derivative. For example, this first correction.
So you explained the first two, but not the logarithm.
Say again?
You explained where the first and second line come from.
No. So So the column is how derivative suppressed it is, and the line is how many loops. Okay. So let's say 2, 1. This is a 2 loop, 1 derivative suppressed. Okay. There's 2 kind of simultaneous expansions in derivatives and in loops.
And this logarithm of t divided by what? Which time scale?
This one? Yeah. So similar to the time scale. These also have time scales. There's a bunch of time scales.
So this is logarithm of t divided by what? Or multiplied by what? I mean, is t measured in seconds or in 10 to the minus 120?
It's absorbable. It's absorbable in other terms. Yeah. So it's.
But shouldn't in any case, it could be very big, right? If they choose bad time scales.
That's right. But then it's just a question of what you're going to affect that.
But this is precisely the question. The fact is that these loop effects act as counter term of the terms in the first line.
Yes, correct. The terms in the first line.
If you change the unit of measure of these, like normalizing,
exactly.
change the mu normalization.
Exactly. Yeah, the time scale I put here is absorbable in these other Wilsonian coefficients, which anyways are not fixed. Okay, however, the coefficient of the log is fixed. In particular, let's look at one of these coefficients. Let's look at the leading. Yeah, so I mentioned that most of these are kind of unknown Wilsonian coefficients, but the leading, these loop effects are instead completely fixed. And I'm going to talk about the leading one just because it's the simplest, but we can look at higher loops too. And its coefficient is completely fixed. So this is the answer. This is in a diffusive system, so it's a bit simpler than a QFT, which has sound modes and so on. You can do this as well in QFT. I'll take the result in a bit, but the coefficient is completely fixed, okay, by the things that appeared in the leading part, the diffusion constant. This is a charge. You can think of this as the specific heat. This depends on thermodynamics, the free energy, and that's it. The coefficient is this is what the coefficient is. So this gives you a time scale, and it's basically it's a short time scale, and it's this in some sense the strong coupling scale of hydrodynamics. It may not be the biggest correction, and in fact, in particular at large n, it's certainly not the biggest correction. But often these higher derivative terms come with larger time scales. But at least it's going to bound the regime of validity of hydrodynamics. Okay, so this gives you a time scale that will bound how early hydrodynamics can emerge. At this time scale, basically, I'm saying it's not consistent. If you give me a set of parameters, transport parameters, diffusion constants, and susceptibilities, I know when these loop effects are large, and it's so hydrodynamics can't emerge. Good. So this is, here I've made very little assumptions. This is kind of for any diffusive system, classical, quantum. It applies to heat diffusion and insulators, or anything. In particular, there's no hbar in this bound, but it has interesting quantum implications, especially if you add a few assumptions and you know something about the equation of states and how these things depend on temperature growth. So now let's apply this to CFTs. So okay, the hydrodynamics of CFTs is quite different. If there's time, I can say a little bit.
Can I ask a quick question?
Yeah. Okay.
How did you get the bound? You just said the loop correction can be too large, but but you got an exact equality. So how large?
Yeah. So I'm saying okay. So we don't have a sharp definition of this equilibration time. So I'm proposing to define it as the largest correction to hydrodynamics.
Oh, I see. So just when it becomes big. Okay.
Here, so this bound will not always be tight. In particular, it's never going to be tight at large end, but we know one correction, and so that bounds the largest. Yeah, it's like exactly. It's
Yeah,
like,
in what
it's
sense
like,
this is different than deciding the scale where the ion Lagrangian breaks down?
it's
In
the
a
same.
sharp-
It's just
can you do
giving
it in a
sharp.
sharp way? Can you tell me the mass of the rod in a sharp way?
No, so yeah, it's hard to relate other. Yeah, I can't determine this in terms of.
But you cannot do that work by D.
No, I
You cannot
understand.
test it.
Yeah, but this is
Yeah, you need to have.
squiggly. It's a squiggly upper bound. It's okay.
Well, you need you need a definition for this time scale, and it's one that doesn't rely on microscopics. It just relies on observables, and you can measure these coefficients. So, and so many of these are really non-trivial, Wilson coefficients. So it's going to be hard to constrain them, but some of them are fixed by the. Okay. So right. So now let's look at the case of CFTs. So here I have in mind a CFT that I place at finite temperature. Okay, so imagine a quantum critical point, and you heat it up. And what's nice here is that the equation of states is completely fixed by scale invariance, okay, up to a dimensionless number. And this kind of dimensionless entropy density this you can get from. This just depends on thermodynamics. You can get from lattice, Euclidean lattice data. It's not a complicated thing to get. It also fixes the diffusion constant in terms of temperature up to a dimensionless number. This is a much less trivial quantity. Okay, we don't know what this is for the 2+1 de-Ising model. It's a transport parameter. But what's nice is that we know the temperature dependence. So I know the scale of this strong coupling scale of hydrodynamics thanks to this exact temperature dependence. So if you plug everything in this bound, you get something that's almost the Planckian bound I was talking about, but not quite. It still depends on these quantities, and in particular on this non-trivial transport parameter. But it's already an interesting bound. So you can actually read this as a bound on diffusion or shear viscosity. So this would be a bound on eta over S in a CFT. That depends on this time scale, this equilibration time that I defined earlier. So it's a bound that relates to observables in hydrodynamics. Okay, the leading shear viscosity and these timescale suppressing subleading coefficients. It's not exactly so. Yeah, the bounds on the shear viscosity have been conjectured for some time. It's not exactly one. The thing on the right hand side, it depends still on this transfer and the equation of states, but it's kind of already. To get the actual Planckian bound without involving these this out of equilibrium physics, the diffusion constant on the right hand side, you can use causality. So causality also leads to interesting constraints on transport, because diffusion naively is acausal at early times, right? Diffusion spreads in this x equals square root of t way, and so it's going to leak out of any light cone. Of course, that's not inconsistent because it's an effective field theory. Diffusion only emerges at late times. But that gives you a bound. It tells you that diffusion can't emerge too soon. Otherwise, it would predict large spectral densities outside of your light cone. This is from these people, and that leads to another simple bound on.
Isn't this the same as saying that if you take a relativistic velocity coming from K over m, when K becomes bigger than m, this is because it's a relative thing.
Yes. Yeah.
So it's a very gross.
It's a very gross, and in fact, yeah.
Very gross thing.
Right. So, well, I mean, it depends how you. So,
the momentum becomes of order of the Compton wavelength of
yes.
the Compton wavelength. Then
Let me say it a bit differently. So, hydrodynamics predicts predicts correlation functions, right, of your stress tensor and so on. It has a very definite form. It has large spectral density in this diffusive cone, and so it receives corrections. But if these corrections are small, then there's no way to cancel, right? You're going to leak outside of the. So that gives, yeah, but indeed, the problem is that, which you were referring to earlier, this is not going to match the definition I gave of the equilibration time, because the corrections in this region are not exactly the ones I was talking about that are kind of following the hydrodynamic mode. So there you kind of lose, you get a squiggle because you're kind of comparing two definitions of the cutoff. But at least parametrically, combining these two things. So what's interesting is that they depend on different powers of the diffusion constants. One of them, right? So basically, the equilibration time is bigger than d, and 1 over d, so it's bigger than 1, up to this factor measuring the equation state. Okay, so this kind of shows parametrically that you can't thermalize arbitrarily fast. One thing one thing to comment on is that you could have hopes to do a little better. So here, there's still this factor that will grow with the number of degrees of freedom. So I think, for 2 plus 1 de-Ising, this is fine. We know this number, it's 1-ish. For QCD, it's 1-ish, and so on. But we don't expect large N systems to thermalize arbitrarily fast either. So you might hope to remove this factor, but the argument I'm giving necessarily becomes weak at large N because I'm bounding these corrections from these fluctuation corrections, which are small at large N. So that's obviously not the best you could do. Let's see, how am I doing with time? I don't see a bunch anywhere. Is it? Okay, perfect. And I started at 2.
Okay, 5.
Okay, good. Yeah, so maybe let me give you a few extra technical details, since you guys I'm sure you like some technical details. So these loop corrections, I kind of took diffusion as a simple example, but you obviously need to do this for fully fledged hydrodynamics. And it turns out that these loop corrections, so they've been studied for a very long time, for 50 years, these fluctuation corrections hydrodynamics, and yet they hadn't quite been done right, or specifically, it was not possible to extract from this existing literature the thing I wanted, the late time corrections to a 2-point function of the stress tensor. Okay. And the point is that in all of these, as far as I can tell, in all the literature, they were studying 0 wave vector observables, okay, because they wanted things like the shear viscosity. And it turns out that the kinematics is very different. So that even the power laws of these corrections are different when you kind of study this region that you could say is kind of close to unshell, right? You're studying kinematics in momentum space close to the pole of your sound mode. This is what you should do if you want to look at real-time physics, because you're going to pick up, this pole. So you should study this regime. In this regime, these corrections are actually completely different. Even the power laws are different. I can try to give a simple explanation. So, you have sound modes in QFTs, and let's say you want to study a 2-point function that propagates from, so this is x and y, propagates from here to here at some time, and it's going to just imagine a kind of loop correction in real time and space. So you're integrating over intermediate points, and the fluctuations along the kind of collinear fluctuations are suppressed. So basically, your integral is going to be dominated by modes that are along the trajectory of your sound mode, roughly, plus fluctuations. The collinear fluctuations have this diffusive broadening, which you might have expected naively. This is very similar to what happens in diffusion. But the transverse fluctuations are actually can go much farther. Basically, just because this exponential is kind of less suppressed if you go in opposite directions. So the power laws are completely different. In momentum space, this means your wave vectors will have a smaller region of soft wave vectors, and so it changes the actual power law that you get. So this is basically how the stress tensor 2-point function looks. So there's this leading sound mode, and then the subleading correction just has a different. It's actually smaller. Loop fluctuation corrections are a little bit smaller than you might have expected from the previous naive arguments. So this is not just academic. So I actually need these for the bound because that's how I'm getting the first correction. But also, these actually imply that shear viscosities are well defined in 2 plus 1 dimension. So for example, the Ising model has a shear viscosity that one should try to determine. I don't think it's known what it is. So in the kind of previous scaling, if you define shear viscosity from the usual 0 wave vector Kubo-like formula, you'll get log divergences in 2+1d. So there's going to be a log running, and at very low energies, it's just going to be fixed by thermodynamics. It's not a free parameter. Whereas if you define it, so in real time and space, the corrections are not logs, they're power law suppressed, and there's a sharp notion of a shear viscosity. So yeah, I thought that was fine.
Sorry, this was like, so this, you're saying essentially how much to complete the loop. So this integral just we transform the equation from here, talking about the
yeah. Integral. So here I'm just for this specific comment, I'm saying the corrections are controlled. They're power law suppressed. Whereas you might have thought that they were log enhanced.
So these are corrections from a loop or from hydrodynamic terms?
From a loop. The hydroderivative terms are suppressed anyways.
So the shear but this is not the shear viscosity.
This is a way to define the shear viscosity. So a naive, if you read a textbook, the way you would define a shear viscosity is this Kubo formula. If you do this in 2+1d, there's a loop effect. There's a loop correction which is log omega. Yeah. Okay. And you can resum the logs, and so it's kind of like marginally irrelevant. So you can resum the logs, and at very low frequency, asymptotically low frequencies, you get something that just depends on thermodynamics. So there's kind of no, you might have thought, oh, there's no well-defined notion of viscosity of a 2+1d QFT. But actually there is. You just have to look at correlators in real time, or you could work, there's several ways of doing it. You could turn on a finite wave vector if you want to work in momentum space, or if you want to actually, do this, you could hit your system, look along the sound front.
What is the shear viscosity in this formula?
It's this gamma. Yeah, it's this gamma. Yeah, it's in the leading term. Yeah. It's the diffusion constant. Okay. Okay, so in the last part, I wanted to tell you a little bit about numerics, where we kind of test these effective field theory statements, in particular these subleading, these more subtle power law corrections to hydrodynamics. So it's hard to simulate QFTs. This will be much simpler systems, lattice systems, and so on. But there's still diffusion, emergence of diffusion in these systems.
Sorry.
Yeah.
Okay. So what is the summary? So you didn't prove the bound yet, right? So you derived some bound, but not quite the one which.
Not yeah, exactly. So you could that's as good as I can do, right? Yeah. You might expect that that you could improve this and not have end dependence, although I think that would require actually bounding the higher derivative corrections to hydrodynamics, which is a harder thing. But I'm saying even without doing any hard, fancy UVIR type constraints, the EFT itself has a strong coupling scale, which tells you hydrodynamics can't emerge too soon.
Sorry, let me see if I can phrase this in another. Take the parameter.
Yes.
The lowest energy, you have one parameter which is f pi. Then you know that this theory, the scattering.
Exactly. Yes. So I'm
saying a couple at 4 pi f pi.
Exactly.
And then below that scale something must happen.
Yes.
So that's the qualitative thing. Then you can say in the infinite tower of operators that exist beyond the leading term.
Yes.
Take the second, we have a coefficient.
Yes.
And then you say, now I want to place a bound on this coefficient. And this I call this bound compared to the absolute bound on the thermalized. They are analogous. I mean, it's a convenient, but you're bounding some coefficients and you're assigning those coefficients some
that's right.
specific meaning. Yes. But this is what.
But even the first statement you made, the first statement of saying, I do Pyne physics, I look at low energy observables, I extract an energy scale f pi, and therefore I have a strong coupling scale of pions.
Well, that's the scale where the scattering phase is order pi.
Right. So you'll have a strong coupling scale.
That's the definition of the scattering phase.
That's right. That's right. And so that something happens at that scale. That statement did not exist in hydrodynamics. So hydrodynamics has been around for a long time, but not with this kind of EFT mindset of saying, low energy observables give you constraints on how early hydrodynamics can emerge. I think that's the thing that was missing. I agree that the statement is pretty obvious from an EFT perspective.
But there's also in the statistical mechanics thing, this is the same thing, right? Yeah.
Yes, but no one made this statement.
I see. So you got to. I see.
Yes.
So you're like the weasel in the rooster. I see.
No, I agree. Yeah, it's from an EFT perspective, it's a fairly standard statement. But it's not very standard to view hydrodynamics as an effective field theory. It's a subtle effective field theory. I put, we'll see. It's an effective field theory on Schwinger-Keldysh. You might, it's a different you might think those are different, but yeah.
I have a question about shear viscosity. Actually.
Okay.
So normally shear viscosity scales like the mean free path.
Yes.
Right. So it diverges in the free field limit.
Yes. Yes.
Is that? I mean, in your formula, it's just this diffusion constant.
Yep.
But the diffusion constant is finite at the free field limit.
No, it also diverges.
Why?
Diffusion constant is, I mean, well, so for a CFT, the shear viscosity is the diffusion constant of
this is
transfer
also
sound.
CFT. Yeah. Okay.
But even in let's say a spin chain, diffusion constant diverge. The same argument you said about shear viscosity. Diffusion constant is basically measuring a mean free time, or a mean free path in a weakly coupled set. They all diverge.
So the stress density function is just okay. Yeah, I think that's okay.
Okay. Yeah, let me tell you a little bit about numerics as well, even though it's kind of slightly different types of, because I think it's nice, again, to bring the CFT mindset into this world of, chaotic systems where you might think not much can be said exactly. So we had this simple picture of hydrodynamics. To make these more specific, more precise predictions systematically, what we really use are these Schwinger-Keldysh effective field theories. I think in the interest of time, I'm actually not going to tell you about those. I know that some people want to hear about them, but these people have already spoken enough during this talk, and we can talk about them. We can talk about them later. The point is just that we have effective field theories that where the degrees of freedom are basically densities, and there's a systematic gradient expansion and fluctuation. So it's kind of similar to, let's say, fine Lagrangian, except it's dissipative. It has some eyes. The unitarity constraints are a little bit different, but we think we can really kind of do the precision physics in these systems. And as probably don't need to convince people here, but effective field theories are useful. You have, even though you don't know coefficients in your effective field theory, they'll tie many observables. For example, nonlinear response I mentioned earlier will be tied to things like linear response, the density dependence of your diffusion constant. Okay, so we wanted to test these things. So let's look. The numerics is simplest and lowest in lower dimensions. What we looked at one-dimensional systems, where the two-point function just looks like this. This is this Gaussian, diffusing Gaussian. This is what it looks at leading order at late times. Okay. Here I wrote it in terms of a scaling variable, x over square root of t, just to make things nice. So this is the leading behavior, but there's, as I mentioned before, there's an infinite tower of corrections. And each of these corrections come with their own scaling functions that you can just compute from the effective field theory. Okay. So this answers Sergei's question of how do you distinguish, some of these terms, logs versus, they all have different scaling functions, and these scaling functions are just, you can compute them. And so here you're really kind of starting to use the predictive power of the effective field theory, because there are going to be Wilsonian coefficients that you don't fix, but the whole you're still predicting entire functions. Okay. You fix a few coefficients, but then you can predict entire functions. So just to give you an example, this leading function is just the Gaussian that we talked about before. This is how diffusion, the leading two-point diffusive function looks like. And this subleading correction, this one loop correction, you can compute it. It has this functional form. And the claim is that this is the same for any diffusive system.
So what is y?
Y is the scaling variable. It's hidden. Yeah. So it's the natural scaling variable in the context of diffusion. Okay. Right. So these things, and again, these coefficients are not universal. They depend on various parameters of your EFT, but you measure them once, and you have this whole function's worth of prediction. So now you can go and test this in systems. So we looked at various lattices and 1+1 dimensions. These are numerical experts. The simplest numerics you can do is just classical systems. So that's kind of a nice place to do these first tests of the effective field theory, where the numerics is done on huge systems. It's very simple numerics. So this numerics that we did is just particles hopping on a lattice, and they hop stochastically based on rules that depend on whether there's particles nearby. So it's an interacting system. It thermalizes, and it turns out, in fact, that in these systems you actually know you can compute the diffusion constant analytically. So even some parameters of the effective field theory are completely fixed. And in fact, so actually the leading behavior and this loop correction are completely fixed by the fact that we have the diffusion constant analytically. So it's a zero parameter test of these effective field theories. So here I'm plotting the 2-point function, density 2-point function as a function of space, or the scaling variable, x over square root of t, so that it kind of, and I'm plotting it like this so that it kind of collapses at late times. Okay, you see the data, early times is blue, late times is yellow, and it collapses towards this Gaussian prediction, the leading order prediction. But you see that there is a small deviation at intermediate times before it kind of fully collapses. So what you can do is now study this small deviation. So you subtract the leading behavior and plot the rest. So this is the data minus the analytic prediction for the leading behavior. Again, blue is early times, yellow is late times, and the dashed black line is the theory prediction with no parameters for this one loop effect. Okay, so here you see really kind of quantitative agreement, almost percent level over a whole scaling function of these effects with zero fitting parameters. So I think this is kind of very nice tests of these. That shows that we can do all these subtle, see all these subtle effects in otherwise chaotic systems. Okay, you can even look at systems where the leading loop term is fine-tuned to 0. We tried to look for these 2 loop effects. That was a little harder to see. Qualitatively, things agreed, but it was a bit harder to be quantitative because now there's also hydroderivative terms that compete at the same order up to the log, and the hydroderivative terms you don't know that they depend on independent Wilsonian coefficients. So there was a little hard. Things worked, but there was a fitting parameter, so it was maybe a bit less. Okay, so these numerics people are excited by this because you can, so classical systems are easy to simulate, but quantum systems are very difficult, and it's hard to do large-scale late times simulations in quantum systems. So these effective field theories are great tools for that, to help you try to extract reliably late time asymptotics in your data without having to spend too much money.
Luca, and
yeah.
this universality that you're seeing here is independent of whether the theory and the relevant scale is classical or quantum.
That's right. This first correction is completely the same.
This one, and instead of higher order, you may have differences.
Yes, there's the first place where there's a small difference, I think, is pretty high order. It's high order in the 2-point function. It's a bit lower order in higher point functions. Where there's a difference between classical and quantum. I think in the 2-point function, it's maybe this term, if I remember well, which has an explicit. It's fixed in terms of these parameters, but there's also an hbar in that.
So that means that if you were to do the computation in QCD,
yeah,
then the things would be controlled by g to the 4th t.
Yeah.
And here you would, for the first time, see g square appearing independently.
I think that's right. Yeah. So yeah, you're saying most transport parameters will be g to the 4th t.
And here now g square will be naked. The coupling of quanta will appear.
That's a good question. Yeah, I'm not.
Because you could take the limit where g to the 4th
yeah.
times t is fixed,
yeah.
and then you send g to 0.
Yeah.
And this should be the classical case, right?
Yeah, I think that might be right, because you would. Yeah, I'd have to think about it. Yeah, but it seems to be pretty hard to see. I mean, so we want to kind of push these tests to actually see quantumness in a thermal state, right? But it's pretty self-leading in the 2-point functions. You have to look at slightly more. Yeah. But in higher point functions, it becomes just the first sub-leading correction. So there maybe. Okay, let's see. So I guess let me wrap up. Maybe I'll just mention work done by Luca, where you can also compute nonlinear response, nonlinear correlation functions. Again, here the predictive power of the EFT comes in. The same vertices that were giving the leading corrections to linear response are what control also control nonlinear response. So you can test these things. You can do 0-parameter tests of these effective field theories, and you can again guide quantum numerics. So this is some fancy quantum system where basically there the statement is that when you do quantum numerics, you can really use all the observables you have access to to extract transport, to extract diffusion constants and so on, because the same parameters enter all of these observables. The EFT kind of ties how these parameters enter these different observables. Okay, very good. So I think I'll stop here and take questions. Thanks for your attention.
So what is this sharp bound on equilibration?
Yeah, so the sharp bound involves transport. It's not quite the Planckian bound. I haven't succeeded in proving the Planckian bound. This is the sharp bound. So it's a bound that involves other transport parameters.
That's universal.
This one is universal. Yeah, this one. The classical systems I mentioned, it's actually, so you can compute the other, you can measure the other timescales, and they were of the in that case they were of the same order. These Wilsonian coefficients that I mentioned. But in general, you might have, there could be parametric separation between the strong coupling scale and the scale of new physics in EFT language. But when there isn't, you expect this bound to be saturated.
But this bound is always weaker than conjectured.
In the conjectured one?
Yes.
Yeah, it depends. Actually, no. It's sometimes stronger. So you can, depending on.
So that means you have a counterexamples to the conjectured bound.
To the conjectured bound?
Yes.
No. The bound is stronger, meaning the conjectured bound is stronger.
Oh, yes, I'm confused about
one example is two-dimensional QFTs at high and low temperature. There you can use this type of argument to prove a very strong bound on equilibration, that the equilibration time diverges as you go to infinite temperature, because in the CFT doesn't equilibrate. So this is maybe not too surprising, but you get these same ideas leads to a much stronger than Planckian.
But can you make it other examples when it's not? Basically, my question is,
yeah.
Can one cook up with this system which would contradict the conjecture bound, playing with these parameters d, prime?
Yes, but there. So this time scale is sometimes much slower. Yeah, the bound is sometimes much weaker. You're saying in those cases, could you find? I think that's related to my. I think not, and that's why I think. So for example, at large n, my bound leaves room for fast thermalization at large, for faster something super Planckian thermalization at large n, which is probably not possible. Although I'm not sure. Yeah.
So what's known about d prime in general? Is it negative, for instance?
In complete general, or you're saying in QFT or?
Well, as general as you think this bound is, what's known about d prime?
No, so this bound holds in spin chains where the d can be any function of density.
So it can
but this, sorry, there should be an absolute value. Yeah, this is. Are you worried about signs or?
Well, that and the fact that it can be zero. I mean,
it can certainly be zero. It can certainly be zero. A case where it's zero, actually, we simulated a case where it's zero. So if you have charge conjugation symmetry, if you're at zero density, let's say you do charge. So for CFTs, I would study energy transport, but let's say you did charge transports at zero density, then d prime would vanish just by n goes to minus n symmetry. And there I would indeed the bound is trivial. But you could go to the two-loop effect and try to get a bound involving d prime. So yeah, no, this, I mean, there's this d can be wildly different functions. Yeah, it depends on the equation of state of your lattice system.
Yeah.
Anything.
Yeah.
Okay, so there is a universal bound that is the equilibration larger than, not smaller than zero, and that's always true. There is this one, but there could be other.
There could be better bounds. Yeah.
This bound is sharp as long as the equilibration is defined in a specific way.
In a specific way, yeah. And it's an observable
This is like
dependence.
I can say, oh, now I'm looking at statistical fluctuation. What is the length scale at which the cubic correlation of the quartic becomes of the order of the quadratic square, which is the scale of non-gaussianity. It's essentially this scale.
It's essentially this.
That, so you chose a specific definition of thermalization.
Yes. But it's one, so
it's like in the Pio-Lagrangian.
Yeah.
I just say, what is the scale where the scattering phase, the one loop becomes of the order of the true level? Is this scale? And I say this is the strong interaction scale.
So I'm not that's the scale I measure, but I'm saying in the language of the Pio-Lagrangian, I would say it's the scale suppressing hydroderivative terms that I'm defining as the equilibration time. And then I'm saying, well, the strong coupling scale bounds that.
Yeah, you can do it with the 2-point function. Or
Yeah.
You did it with
Yes.
the 2-point function.
That's
You
right,
could have
that's
done it with the 4-point function.
You could no. So indeed, there's some arbitrariness in how in what.
And
observable
derivative in
features-
the 4-point function.
I'm saying there's a
That's it.
preferred, so the other definitions, your previous definitions relied on macroscopics, right? You need ultimate picture of quasi-particles, how long does it take for scattering at 45-degree angle, right? This definition, at least I can use it in a strongly interacting CFT, a spin chain, QCD, okay, you have density operator, or T00, let's say. You look at a 2-point function, these are all, these you could measure them for various CFTs, they're CFT data. It's a sharp definition. I agree it's a bit arbitrary.
You can use it sharp with these other guys, less so with us.
I mean, it is a sharp definition. I think it's a bit arbitrary. That's what you're complaining about.
Yeah, exactly.
It's a bit arbitrary.
We've been doing that for quite a long time.
Yes, yes. But not in hydrodynamics.
No.
Yes.
What about the generalizing sharper bounds like this UVIR
Yes.
and bounds with simplification?
Yeah. So
Prospect for that?
sorry.
The prospect to bound is A01, A02.
So that's So there's been indeed a lot of efforts on doing this in the spirit of how it's done in regular vector field theories. So one issue
is done sharply at weak coupling, at zero coupling.
No,
constraints.
No. So if your EFT has irrelevant corrections, the first few bounds aren't
The first one.
The first one.
The other
exactly.
ones are all.
That's what I'm
based
talking
on
about.
weak
That's what I'm talking
coupling.
about. The first bound is not polluted by cuts, IR cuts, and you, as some people in this room showed, and but the problem in hydro is the following: it's as if you had marginal interactions, meaning it's as if because you have spectral densities down to zero frequency. So it's as if the cuts, basically, the fact that IR cuts kill the bounds happens down to the first bound, So these you can write down some rules in hydrodynamics, but you need to subtract these IR divergences, and then you lose positivity. But the subtractions are at the same order as the things you want to bounce. If you play with arcs and so on, you don't save anything. But yeah,
I mean, in the case where your bound doesn't become strong, which is the technique about weak coupling, that's 1/n
Yep.
of the block, then you can neglect this or not.
neglect.
Okay, you can neglect these cuts become small, like in this large effective theory bound.
No, because the cuts. Sorry, in hydro, the cuts aren't coming from loops. You have imaginary parts of spectral densities just because of dissipation.
Of course.
Yeah. So that's why you lose. You don't have a set separation of scales. The PFT parameters you want to extract using the contours and so on, and the imaginary parts. But I still have hopes for these types of things. I think you need. I've been thinking about this for some time. That the most obvious things don't work, but I think there should be not anything should go. There should be naturalness type constraints on these Wilsonian coefficients, but it's not completely obvious what the tools should.
Take out your body. There's water. Yeah.